Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome to this presentation. It's a quick throw together in the last couple of hours and I really wanted to get this out. There's several things that I had been holding off on because really I wanted to give one Andrea Rossi a chance to up his game and show the world what he has, and to reveal how it works. And we had a presentation yesterday. I'm not sure it achieved those goals. However, there was sufficient in there to confirm my hypothesis that I've had for a couple of years, and I'm going to go through that today. I have been talking for many years about what goes up must come down, and I've done a couple of presentations on, or at least one presentation on my remoteview.icu blog, and there was meant to be two more sections to that. I'm going to dig into a couple of things that were going to be in those presentations because it's necessary to get the message across today, and also some other data that is very, very relevant that's been recent, and I have talked about it, but I don't know whether anyone's grasped the significance. However, it's an emerging pattern which is all entirely consistent with the way that we believe these things can be utilized. And yes, they can produce a variation of heat, light, and electricity. And there are, different proportions of which you can get those out. Although I would argue that if you push it so far, there will be certain outcomes which are undesirable, and the ones that we are well aware of. And there will also be some transmutation, but you could certainly argue, as I will show you today, that this technology would allow for rectification of energy in a way that would not require nuclear reactions to take place to yield useful work. And you can see all of this going on in EVO Blaster. This was the very first Vega experiment video that was shared, and when I saw it, I knew it was so significant it had to be shared, and I've left it hanging out there with a couple of open questions, and we're going to dig into that, and I'm going to explain that video, which was actually published on December the 10th, December the 10th, 2020. So this is the year anniversary of that video, and I committed myself some time ago that I would do this video today, and it just so happens that it's extremely relevant, and you'll know why when you see it. Anyway, so how is everyone? Can you hear me? Excellent. I've got audio good, excellent, and you've got to see my face, but that's okay too, I guess. Right, so I'm calling this presentation Explaining the SKL, and for those that don't know, this is one of a number of different abbreviations for Sven Kullander electric or light or whatever. There's ones where there's an ED at the end, or a SKLEP, so that is a Czech word for seller or a Polish word for shop, but I guess it means Sven Kullander electric something, I don't know, but anyway, these are the naming conventions that have been derived from an original name for various technologies of one Andrea Rossi's so-called ECAT. Anyway, it's been speculated for a very, very long time that this was a riff on the sort of Chernetsky, the sort of ball lightning, the plasma-focused device of Ken Shoulders, which was supposedly replicated, I think, at Edwards Air Force Base a long time ago and produced a COP of 10. I don't know whether it went on from that. This is the rumors that I have heard. And anyway, I'm going to walk through why I believe we have extremely strong evidence spanning the history of the MFMP for why this could occur. And if Rossi has not achieved it, then it certainly has been achieved in various aspects by ourselves and by other researchers. And there are tantalizing tidbits that I've talked about over the many years of the project that would point to this being a realizable thing. But down the bottom I have EVOs, which in this case, in my view, will be electrons and xenon. So electrons are the electrum validium, the EV, which is just the strong or collective bound electrons. And the xenon ions would be the ions that cause the production of charge clusters, high density charge clusters, and because something more interesting goes on, we change the name to exotic vacuum objects. So our exotic vacuum objects in this case will have at least electrons and, in my view, xenon. And if this is driven sufficiently, this will produce UV light and deep UV light. And in fact, I will argue that it will also produce soft X-rays, even through to some hard X-rays. This will lead to photoionization of the xenon. And by varying the stimulation, you will be able to produce, therefore, heat and or light and or electricity. You know, there will be various aspects that will be able to be produced there. Okay, so and over on the right here, we can see, if I get my mouse working on the right computer, yes. So we can see over here the VEGA-EVO Blaster front frame by Henk. And the video from MFMB. I'm going to talk about that. But before we go into that, I want to talk about Project Fedora, which was very nicely supported by the crowd. And this was, if you recall, in January 2015. Well, in fact, actually, it was a number of years we had been trying to catch up with Piantelli, having been to ICCF 12, and there was no response. And then we started to consider replicating the original sort of what we could gather from what a Hotcat, or not, a sort of a Parkhomov type reactor would be, I think at the end of 2014. And out of the blue, we got an invite from one Francesco Piantelli, Professor Francesco Piantelli, formerly of University di Siena. And we went and visited him, myself and Mathieu Villat, and we arranged that we would go back again in the beginning of the year, assuming we could get the money together. And the community came through and raised sufficient money in just 7 days for 7 people to come from 7 countries with all kinds of equipment in order to test his apparatus and to record what he had to say about the technology. Well, there was 2 things in that event that really stuck in my mind. I've talked about them a lot over the years, but one of them was in January 2015. I think it was on maybe the 2nd or 3rd day we were there. Francesco Piantelli told us that when he was turning on his reactor at the critical point, he was bending over, and this is one of these Focardi-Piantelli type reactors, the classic one that is in his original patent and in a lot of the 1990s work. He was bending over sometime probably in the early 1990s, turning on this reactor, and he had his shoulder in a position, so this part of the shoulder is, he did this, he described it by tapping on his shoulder, and he was leaning over, and there it's the tube, and where you have the tube, there is a pass-through, and this pass-through was made of like borosilicate glass, so you could melt it and get it in there or whatever, and put the various power and monitoring electrodes through there. And he had this emission, some kind of emission that gave him a very severe burn on his shoulder. Now, the implication of this is because it had to pass through that glass light, that glass window, and otherwise there was multiple layers of thick steel. So if it was some sort of X-rays, it wouldn't probably be able to get through there. But it would appear to be that this was some kind of intense UV. And when I say intense, if it was a quartz pass-through, then pure quartz, then maybe less intense UV could get through. But because it was borosilicate, this would mean it would have to be more intense UV to give him this kind of burn. And it's quite likely that that might be coherent. But anyway, So that is that, and I will take you to the next slide, which is in this journey, and I will be talking here about the ECHO reactor that we saw in America. In India, sorry. Sorry, Suhas Ralkar. And this is my first of the slides, what goes up must come down. Now, this was plasma flow discharge into a steel rebar in the experiment that we witnessed, that is Dr. George Eagley and I. And so I'm going to get the video up here, hopefully, and I can show you, maybe. Let's see if we can do this. I need to pull up a video here, so let's see. Give me a second. I hope we don't have any adverts, but we might have some adverts. Yay, that one. And we can go to Echo. Okay, so we're looking for Echo, and I'm going to show all. And the video I'm looking for is one of these ones. So this Echo Sparks is good enough. And in fact, it was just shortly after this. So I hypothesized that, you know, if exotic vacuum objects were being formed and they, according to Ken Shoulders, can go and live in metals and do that indefinitely. Sorry about the advert here. I have to kill that. So let's go over here so we don't have any copyright infringements. And we'll kill the audio because we don't want that either. Oh dear. Right. So this is this video. You probably only need to see the visuals here, but you can go and have a look at it in your own time. So this was published on the 14th of September 2017. So here we go. This is the video, and this is a water flowing down. This is the cathode. The anode is the actual steel rebar, and you have this flashing here. And there's a noticeable change at some point. So I'm going to speed this on to where the change occurs. It gets quite brighter, quite a lot brighter in the center here at some point. Very, very suddenly, it changes its color. So it goes from this constant yellow to a much whiter look. That you see, it suddenly becomes whiter and orange, and then much, much whiter, and suddenly goes, right, okay, we've got to stop. Right? So very, very shortly after this. Not that shortly, but a little time. There we go. So it comes out and we have this sparking, and I've done a lot of videos. Okay, so what happened after this is this cooled down, and we turned off all the apparatus, disconnected any sort of power leads or whatever. And then what I did was I got a a multimeter and attached it to ground on one side, and we put the probe on here. And we registered 1.3 volts. And this is all published after we came back by Dr. George Eagley in Infinite Energy. So this was my hypothesis, that the charge clusters were going in here and that they could be captured and released. And we, in fact, did see in this insulated piece of iron, when it went through a multimeter, we saw this at 1.3 volts. So that for me was an interesting finding. And it was kind of like a win first time. So it was very satisfying. It's one of those moments when your theory kind of works out. And so after apparatus was switched off, I planned to attach a multimeter to the iron, and we registered 1.3 volts, and it's published by Dr. George Eagley. And later in May 2019, Bogdanovich et al. At the Moscow Plasma Physics Nuclear Research Laboratory, he published observations of long-lived plasmoids in plasma flow discharge experiments. So he is saying that in a very similar system to the one that you just saw, on the metal after the experiment was over, they observed these plasmoids running around, and in their case for up to 2 days. And so, you know, these plasmoids, in my view, have coherent electrons in them, and they have a superconducting ring current, and that's why they can live for a very long time. They emit light because that's something that they do, and we're going to get onto that. But anyway, I hypothesized there were some in there, and that is why we did our experiment, and it would appear that we got these this 1.3 volts detected. Okay. So the next time was in September 2017, and this is my second what goes up must come down. And basically in September 2017, I recognized something in line reactor crust. It was amorphous cupric oxide, and therefore must have cooled at over 1000 degrees per second. This is the second thing that we learned from Piantelli, and it's called splat cooling. It's been used in LENR and other technologies. It's where you want to create an amorphous material with no crystal structure. And we observed that. So I'm going to try and dig up the mining diamonds with lion presentation, because it's in there, and we will be able to see what I'm talking about and why that's important. So just give me, like, it's got a little bit broken in at times because I am building this on the fly with you. So let me just get that. So yeah, okay. So what it is, so for those that don't know the line experiment, it is here, and this was built by Looking for Heat. It's kind of like a folded glow stick experiment. And you put a control sometimes and an active reactor over here. It uses diamond pads from the 3M dia pads. They are loaded, baked at 200 degrees C for a week, and they are put into a aluminium camping pan, and they were immersed into, as soon as they pulled out the oven, into deuterium oxide. And that was then 10 of those were soaked and then put into the reactors, which looked a bit like this. Now note, this is the reactor core, and around this was 2 sets of copper wire, and this is the material that we are interested in. This is, according to the Lion author, just a means of thermal coupling between the quartz, which you can see here, the quartz here, and the inner core here. So you can see a bit of the copper winding on this one here. So it's just, in his view, was for coupling that. Now there's many reasons why this was inadvertently a very good decision on his part. But anyway, we can go down. So there's 2 things. He thought it was running at around about 800 degrees C. We later found in different experiments it was running up to about 1050 degrees C. This is critical because you need to go over that temperature to create the relic neutrino equivalence, according to Alexander Parkhomov. And we also found that in our glowstick 5.2 we had to go over 1000 degrees C before we saw our signal, which we will come on to in a little while. But anyway, what he did was, post-experiment, he turned the power supply off to the reactor, and he attached this 12 volt 20 watt bulb, and he connected it to the reactor bolt end and a pre-discharged drain, whatever that might be, and there was a sudden crackling sound, and it sounded like a cross between scrunching up a crisp packet and the sound made by one of those large plastic storage bags you place your clothes in over winter, seal, and then suck out the air with a vacuum cleaner. With no power connected, the bulb is claimed to have been illuminated to normal brightness for over 30 minutes, constituting over 10 watt hours. So there we go. That is the light bulb. And here is the core in question. And you can see the copper winding here. This is copper oxide, cuprous oxide, and this is mostly cupric oxide, the Cu2O in here. And this is the material in question because I looked at this up close, and when I go in even closer, you can see that it changes with exposure to light when the video decides to play. There we go. It's got a very bizarre response to light, but this is the cuprous oxide. This is what it should look like normally, and this is just smashed up parts of it, and it didn't have any crystal structure. These are smashed up, like it's like a glass that's been smashed up, so it's not so much crystals, although I called it crystals there. What it actually looked like under the microscope was this, completely glassy, and this is why I assumed that it had cooled at around 1000 degrees per second for this to have occurred. And so at the time I was saying, and you can go back into my comments on ECAT World, I mentioned that I kept saying what goes up must come down, and explaining that I believe this technology can make things hot, but it could also make things extremely cold, because at the time that I was saying that, I thought the top temperature of the reactor was 800 degrees, and he's describing over a couple of seconds all this air rushing in to where the tube was, sucking in, which means it must have changed temperature hugely. And then crackling is like what happens when you get a glass forming, and but it doesn't have time to there's tensions build up, and it's freezing very, very quickly, and so it cracks. And you get the fissures in there, and so that was the whole crackling sound going on. So I'm thinking, well, you know, this must have been cooling. So if it was cooling about 1,000 degrees a second, and it was about 800 degrees, I thought, if this is lasting for a couple of seconds, then, you know, there isn't many thousands of degrees to go 1,000 degrees per second for 2 seconds. So it must have gone well below zero. So I made a point of saying that this goes very, very cold. And so I talked about the different phase things here. But actually what happened was I sent these images here to Alan Goldwater, and actually I then went and saw Suhas Ralkar again, and he said, what's this little thing down here in this bottom? And I thought, I don't know, Alan, but I'm going to have to wait till I can get back to Czech and after I've been in India, and we'll have a look at it on the SEM. And that is where we found our beautiful lion tracks. These are these monopole structures, probably on a cluster, which is spinning around and going through this beautifully glassy cupric oxide. And so here we had a series of things. We had something that looked like it was cooling at 1,000 degrees per second. Okay, then something that was producing or being able to, with no input energy at that moment, able to light a light bulb for a long period of time, a halogen light bulb. And then lastly, it was able, it had these, what were very clear to be, in my view, strange radiation tracks. And so what do we know? Well, strange radiation tracks are related to exotic vacuum objects. So we know from Ken Shoulder's writings that exotic vacuum objects can stay in metals. So I came up with this hypothesis, and here's the overall track with a lion, the lion track overlaid with an echo track, which got during the course of the same year, and so the structure is almost exactly the same. This was captured on the Logitech 910C, which I actually have here. This little device here, this little beauty, did that image there, and using Cosmic Rayfinder, and I got the author to adjust the software to help produce this. Anyway, so this is the track that was captured in exact matchup, and Keith Fredericks worked out the track and so on, and the fact that it was a standard type of length of strange radiation track. So anyway, that's the point. So we see that we've got a cavitation system and a deuterium nickel system producing exotic vacuum objects, and that it is clearly in the metal. And so my hypothesis is that, and Ken Shoulders has this in one of his writings, that the electrons can go into the exotic vacuum object. And when they're in the exotic vacuum object, and he can change the charge from 100 billion or 1 billion to 1. And what this must mean is that they are becoming coherent. So they're becoming like one wave function. And in the process of doing that, Ken Shoulders says they release UV, and we'll talk about this later, and soft X-rays. And so what's interesting about the UV? Well, Piantelli saw the UV. And so if that's the case, it's releasing energy like a plasma does when it goes to a gas, like a gas does when it goes to a liquid, like a liquid does when it goes to a solid. This is going from, well, you know, kind of like whatever it is. In this case, it's electrons and maybe nickel ions or deuterium. And maybe it's going to some sort of solid densities. And he describes that the electrons become solid density of material. And so you are having a condensation process, and the energy is being released in photons of various degrees that are at high energy. So he then says that if you disrupt an exotic vacuum object, it will then destabilize. He calls it disheveling, and then the electrons will go back into the world of normal electrons. And why is that very interesting? Well, for them to go back to normal electrons, they must get their kinetic energy back to become it's like if you want to take ice and make it water, you have to put energy in, don't you? If you want to make water into water gas, you have to put energy in, don't you? If you want to make water gas into a plasma, you have to put energy in. So you have to put energy back into it. So what do we know about what happened with the Lion reactor? Well, we know that it was lighting a light bulb. Okay, we know that it was freezing at a very fast rate, and we didn't really know what that is at that time, but we knew that it was making a glassy state here, and we know that there's exotic vacuum objects involved. Now, I was saying this over and over and over again on ECAT World and on various other channels on the MFMP's quantumheat.org site, and someone called Dr. Bob, and I don't know whether you know his real name, but he calls himself Dr. Bob. He was working with Looking for Heat, and he said to me, "This is very interesting, Bob. Why are you saying all these things about what goes up must come down, and why are you saying that you expect this technology to be able to super cool things?" So I explained a bit, and he said, "Well, this is curious because we've looked at the data card that Lion sent us back because he had no means of analyzing it or whatever, and we plotted the temperature curves up to the point that the reactor, shortly after the experiment was over, and something remarkable showed up." So I'm now going to show you one slide from O-Day. It's a slide you haven't seen, so I've got to actually go and get that presentation and dig out that slide and show you that. So we're nearly through O-Day slides. This is in fact, it's popped up on the slide. There we go. The universe is aligning. So, so I haven't changed this slide since the beginning of 2008. I'm just going to read you it now. I don't even know what it says. What happened to the Lions? Baby charge clusters, exotic vacuum objects, in the core formed from spin vortex solitons, there we go, from deuterium oxide diamond emissions with bosons such as neutrino and antineutrino, positron and electron. So that would be the material that you would need to make a itonic cluster. Deuteron nucleus of 12 and 12C nucleus and all but 61 nickel isotopes. Electrons are stripped into the soliton, and I'm writing this at the end of 2017, beginning of 2018, and this is actually what we saw in that paper that was released earlier in April this year, which I talked about, this simulation paper, the international collaboration. The treated diapad is the ovary, potentially pumping out millions of male-female babies in a second. Oh, I like the way I wrote that. That's just, well done me. Migration of babies to highly conductive copper outside of the core, possibly conducting through Bolt. As the baby is a fermion, it can hide in conduction band. Black holes, this is the exotic vacuum object, charge pumped by photons and phonons from the heater in the electric field. Other available bosons, composite bosons, including copper, fermions stripped to build soliton. So there we go. Larger clusters form with yin-yang equidistant pairs and build in a fractal fashion. Eating of matter and production of new elements from exotic vacuum structures and jellification, and you can see that on the material. Excess heat from thermalization of 2 to 50 kiloelectron volts shed from the charge clusters, as well as Hawking radiation released as beam or black hole's axis. So this is my thinking at the time, so you can see it. This is insight into my thinking at the end of 2017. David Hudson reported Ormus gives out more heat than put in, and we know that's a orbital spin structure change. When drain attached, near instant heating, oxidation followed by instantaneous cooling to near absolute zero, as bosons released from the black hole suck from the exotic vacuum object, suck phonons heat to replace the lost energy to reconstitute the atoms, and causes cold electricity. So it's not only reconstituting the atoms, it's reconstituting the electrons. Negative voltage spike if electron source applied to provide electrons to those bosons that are deficient. So there's two different things here. You've got billions and billions of electrons coming out, and then you also have the ions coming out, and the ions need to recapture electrons as well. Now, what was it that Dr. Bob sent me, because they found it very curious at looking for heat, and they had no explanation for it, and he said, "Oh, why are you going on about this instantaneous cooling?" Well, that was slide 73 of O-Day, which has not been seen before. This is slide 74 of O-Day, and here is the chart. A temperature profile from a Lion experiment received 5th of February 2018. So you can see how early this was. Anyway, so you can see the profile that he talks about in his protocol, and then his cycling up here, and this apparently, as far as we know, is when he attaches the bolt. Okay, so very, very instantaneously, a straight line up, you have an increase in temperature. The temperature thermally goes up, and then it goes straight down to about minus 273 degrees centigrade. Minus 273 degrees centigrade. What is that? That's all the temperatures you can get. That's it. This is absolute zero. It sucked out the energy. And so if this core at that point, and one of these cores, the copper in here, was going from, let's say we now know it was around about 1050 degrees C, and then it's going down to absolute zero. Well, the electrons are not going to be satisfied, the ions are not going to be satisfied. All of that material has to gain back even more heat, and it's not sufficient with the bulk of the reactor. It sucks in even more heat, and it's extracting the heat from the air. And as the air comes in, it's probably freezing in here. And I will show you people that are claiming that if you get a spark gap right with a Tesla coil, you will actually get ice crystals forming on the anode side. And so this is consistent with the observation in the Lion reactor. So that is why I was saying what goes up must come down. Okay, so we can drop now out of, show you that again. So the temperature goes up, he does his cycling, he goes like this, he turns it off, he attaches the bulb, you've got to shoot up, but very instantaneously it then goes down. Okay, so that is the experiment data there. Okay. Right, so let me go back to the other presentation. I don't think there's anything more I want from O-Day today. So you had another 2 slides from O-Day. I like reading my old thinking there. Okay. Oh dear. And of course, we have to give credit to the Lion author, because it was in here that I started seeing these 2 spots. So if you recall, the reactor went into this X-ray chamber, so dental X-rays. And if we go forward, there were these 2 X-rays, and there were these 2 spots. Okay, very distinct. So what does this mean? It means that it is producing X-rays. It is producing X-rays. So we have UV and X-rays. UV and X-rays. By the end of 2017, very early days in 2018, we know that something that is producing exotic vacuum objects is producing soliton pairs, or magnetic flux loops, that are have X-rays or can influence X-ray paper. Celluloid. And here it is. And so I went on the whole hypothesis of the sort of soliton here, and the fact that it's like this, and the fact that I observed these things in the ultrasonic cavitation thing that I was talking about just a few days ago. And here's a soliton that's very clear, rather than the one that I showed you that had the same structure as the plasmoid that was observed on the Amasa gas treated tungsten. And we also observed this on the Echo exposed PET bottle here, with these solitons impacting on this PET bottle and leaving these wonderful traces that we've discussed in the past. And then John Hutchison sent me this thing, and then we saw this with the solitons here on changing the copper to iron in this particular material. Okay, so I'm going to step out now from this particular experiment. I'm going to go back to where we were. Okay, so we're back into today's presentation here. So this is I recognized something in Lion reactor crust and was amorphous cupric oxide, and therefore must have cooled at over 1,000 degrees per second, something we learnt from Piantelli. We held off until Rossi had his presentation. We really wanted Rossi to deliver in late in September 2017. So we held off. It wasn't until the beginning of 2018 that we started rolling out the findings from the Lion reactor. But you know, we were just very disappointed in I think it was October or November 2017. But anyway, we gave him an opportunity to come through, and that wasn't done. So anyway, we showed that the Lion paw prints in the cupric oxide and many other signs that EVOs were massively present in the reactor. And really, it was so important for the Lion author to share his reactors and for the crowd to support the work to analyze those, because it really laid the foundation for connecting all these concepts together. And it was years before I came across the Solin patent, which we will talk about, which showed all of the observations that we had observed in here were already in the 1992 patent of Solin for his quantum coherent nuclear reactor. So along with the description of air sucking sound and 20-watt bulb being lit, it was clear stored electrons in charge clusters were being released. So we have stored electrons in something that obviously, in my view, had to have released thermal energy in order to condense into a coherent structure that is able to persist in that state because it has superfluidity and superconductivity. It is able to get down to a level of charge that is so low that it's able to walk right through things, as Ken Shoulders said. And when it walks right through things, it was going in and it was getting stuck in the copper. It was building up in this highly conductive material. And when the experiment was over, it was disrupted in a way that they disheveled. There was a burst of heat up, and then there was this intense cooling effect. And the electrons that were then coming back into the normal electron space were able to light the light bulb. So there's two things there. One, the electrons coming out, and then the ions wanting the electrons back. So there's two ways that this can achieve this electron flux. Okay, so now I must talk about VEGA-EVO Blaster. What goes up must come down. And this is the third of the what goes up must come down topics here. And I'm actually going to have to dig up that video, and we're going to play that through. So I'm going to go back here and I'm going to try and find where that video is. Give me a second. How is everyone? Okay. I'm honestly tired of waiting. I might even announce a competition at the end of this and a way to deliver the competition, which is quite novel. And I just think of it on the way, running up here in my thick winter jacket. But we'll see. What am I looking for? I'm looking for Evo Blaster. There we go. Okay. Now I might actually have somewhere around here the actual cathode, or anode rather. Is it? Not there. I do have it around here somewhere. Maybe it's up here. I don't have it immediately to hand. You just have to trust me. I do have it here somewhere. Okay, anyway. All right. Anyway, it's not so important. Okay, so what are you looking here? This here is the VEGA experiment of Henk. And in the Vega Valley book, which I will definitely be doing, possibly launching on Sunday or early next week, the Kickstarter for, you will see the first photos of the outside of this reactor and possibly even a schematic. But anyway, the actual reactor inside, if you can imagine, this is almost like a hemisphere and it's made of mild steel, so it's magnetic. And this is effectively all cathode. And here it's got an anode. Okay, it's screened with some quartz tubing, and at the end it has a nut, and around it I asked for tungsten wire. So there's tungsten wire around here, and I wanted to try and accelerate the effect that was going to be achieved, and I asked for this to be coated in some potassium salt or whatever, and it was chosen by Henk to use potassium hydroxide, which is absolutely great because it doesn't have carbon in it, so we like that. And the view, therefore, was that potassium has one of the lowest work functions. Remember that, work functions. And so what does that mean? It means that it's good at photoionization. And also, if we are creating exotic vacuum objects, as we showed in the Yu paper, I think it's Yu et al., the one that I was discussing the other day, if we can get 3.6 trillion volts per meter and 1,000 Teslas in a 46 micron plasmoid exotic vacuum object, soliton, then this might grab electrons, condense them into an intense double layer. In that case, they will cohere. You'll get coherent electrons, but their velocity will be extremely fast. What does that mean? You have collisions that are extremely fast, not only between the electrons, but the ions also. What does that lead to? That leads to, my friends, the production of cold relic neutrino equivalents, cold neutrinos, and antineutrinos. What does that lead to? That leads to the production of itonic clusters. Within the EVO, this leads to itonic hydrogen. If you have it in here, we do have it because it has some residual air. But what you're seeing, this purple glow, is because it's got nitrogen from the residual air in there. And that is also a very good fuel for LENR, as I've described, by calculating how you get from natural air for ball lightning that's synthesized in the air to the spectrum that you would get from ball lightning and synthesizing iron crenellated microspheres, as observed in Hessdalen. So you can get that from using nitrogen and oxygen in the air. And so what you are looking at here is, so once you've got that and you've got an intense magnetic flux that's grabbing ions of material in there with input neutrinos, you will get forced decay of the potassium-40 in there. That was my concept for this experiment. So I said, look, we need to get the potassium in there, blah, blah, blah. And so you have this idea that it's going to do the inverse beta decay of the potassium-40. It's something like 0.02% of potassium, something like that. You can go and check it. It's easy to look up. And that, if it does do that, it will produce 1.551 million electron volt beta particles. They will come out and ionize a lot of air. What does that do? That produces a lot of electrons. The electrons then want to go to the anode, where there is an exotic vacuum object building. It will cause the double layer on that structure, which is meshing and self-organizing together, to harness those electrons that are coming in and build it further, building very intense production of exotic vacuum objects. Not only that, the use of tungsten there is important too, because it's a good electron emitter. So the combination of the tungsten wire and the exotic vacuum objects and the process of those exotic vacuum objects causing the inverse beta decay of the potassium, accelerating the process to a point where it might start causing fissioning of the tungsten, which it would appear that we've observed in a number of different experiments, and I've talked about those. The whole smorgasbord of thing there was to generate a large volume of exotic vacuum objects. Okay. So this was basically one of the first videos that Henk sent back after the sort of... he said, what can I do? I said, do this, and do this for this reasons. And this is the video. Okay, so what are you seeing there? In fact, let's go and have a look what I wrote on my blog about that 1 year ago today. And it's the first video, Evo. There we go. Okay, so on the blog, I said VEGA-EVO Blaster, Exotic Vacuum Object Blaster. What is Vega? What is it showing us? What can we learn from it? Developing. So that was my first little teaser, and for me this is still probably the most important video of the Vega series. The very, very first video. Okay, so why am I so keen on talking about this video? Well, the idea is that the cathode here is a big cathode, and the only place that the electrons can travel to is this very small anode, which is in the sort of focal point of this parabolic disc-shaped cathode. And so when it gets here, it finds it has to bunch, and it has also the tungsten and the potassium hydroxide here. So the whole combination of things going on, which are forcing production of exotic vacuum objects. Now, if exotic vacuum objects become neutral, they can go wherever they like. Now, imagine one is born here on the anode and travels somewhere and then hits the cathode, and it's a what do they call it? An impedance change. And Ken Shoulder says when you have an impedance change, then like when you're going through different materials, or going from, let's say, air to metal, or air to glass, or semiconductor to conductor, or insulator, then there will be an impedance change, and this will dishevel the exotic vacuum object. And so when he sent me this video, it was like more than I could have possibly imagined to come out of a hypothesis. And I want to show you. Let's look. Okay, so let's. What you are seeing here is the camera is changing its aperture and showing you the hot area of the tank below of the tank base of the cathode. Okay, and when we play forward. Okay, so did you see that flash up there? So let's just rewind it. Okay, so we'll look at this area up here. That's not a good one because there was already one there earlier. Let's find another one. Oh, that one down there. Okay, you see that one? Just came down there. Find one that's more in the frame. One around there, that one. Okay, that one there. Okay. Now, what has happened? What has happened? Let's wind it back. Okay, so we're looking at this area up here. There. Okay, so what has happened? Well, I believe that a neutral EVO has formed somewhere in the environment, probably synthesized here, and it's come down, hits the impedance change, which is the cathode, and it's disheveled it. And when it's disheveled it, it's gone from a coherent, infinitesimally small thing, maybe in the 1 micron scale or much smaller than that, maybe in the nanometric scales, and it's disheveled, and the electrons have returned to their normal electron state, which means they have Coulombic repulsion, thank you, Dr. Graham Hubler, with the interference at ICCF 23. Yes, there is a Coulombic explosion of the electrons that have come from the coherent state to the incoherent state, which is where they are individual electrons expressing their individual negative charge, and they have Coulombic repulsion. But they have no kinetic or thermal energy. They have to gain that back. And so do the ions that are contained within there. And so do the ions. And what you get is a spherical, completely spherical explosion. Completely spherical explosion. Except you've got a surface. So it goes out like that, but on the surface it can't go in. But all of the material hitting the surface, whether they are ions or they are electrons, are super duper duper needing, they're very needy for thermal energy. And so what's happening is that this black spot up here is created just as the cooling occurred in the Lion experiment. It instantaneously cools this to, in my view, probably absolute zero. Absolute zero. And if you play on, let's look at this spot, okay? If we play on, over the next period of time, you will see that this spot comes back into thermal equilibrium with the rest of the chamber. Okay? This video is so mind-bendingly important in my understanding of this process. So let's see if we can find a couple other examples. The whole thing is replete with it. So there's one there, right in a very bright area. Another one there. Look, you see it just returns over a period of time to the normal thermal temperature of the rest of the environment eventually. So this is why I again started going on about what goes up must come down. Now, my assumption, or rather my educated statement that this was a Coulombic explosion well predates the paper of Dr. Graham Hubler at ICCF 23. I said that as the electrons are going out, they're moving out spherically. And a charge moving in a direction will create electromagnetic waves. What does this create? It creates an electromagnetic pulse, an EMP. And this is specifically a paper that is written by Ken Shoulders. It's fluidized electrons to create an EMP. It's one of his papers. It's something akin to that. And I've discussed this in the past, where the coherent fluidized electrons are disheveled, they become normal electrons, they coulombically repel, and they move outwards, and they produce an electromagnetic pulse. And I said to Henk, I said, you need to now get a radio, tune it between stations, just as John Hutchison was doing in the late 1970s, to work out when his experiments were in the right zone, and listen for the pops. Listen for the pops. And sure enough, we have a video where, and I think I've shared it, where the pops are in sync pretty much instantaneously with the flashes on the video, because he's got like the camera here and he's got the radio here and he's recording the pops and so forth. So you've not only got the audio here, you've also got the pop, the crack on the radio. So you have complete consistency with the claims of Ken Shoulders, and between something that becomes disheveled, it produces a Coulombic explosion, it produces an EMP which can be picked up by a radio. Same thing that was observed in the experiments by John Hutchison that inspired the work of Ken Shoulders. And so these things are all aligning together. Now, the other thing you need to think about is the explosive potential of that. And this is something that Ken talks about, where basically 1 cc of fluidized electrons could basically vanquish a 10 by 10 by 10 meter cube or something of whatever's there, whatever. It's horrendous, unimaginably terrible weapons. Okay, and you can see what it did to the Lion, cracking that up, as very, very, very little ones, extremely little ones, are disheveling. And Alexander Shishkin, in his, maybe I'll pick that up. It's called A New Type of Penetrating Radiation, because we're going to need it anyway. Getting there. Okay. We'll refer to this presentation shortly. Okay. So anyway. So, where are we in our journey here? Hopefully we're here. Okay. So yes, this is VEGA-EVO Blaster. So I just want to see if there's anything else I need to show. So that was VEGA-EVO Blaster. And let me just see what. Right, so the next point I want to make is that John Hutchison used a high-intensity discharge xenon bulb, a high-intensity discharge xenon bulb. And I published a video from the Hutchison lab in Germany, January the 7th, 2018. And so I'm going to go and dig that video up. If you give me just a second. Okay. Is that this one? Oh, whether it's this one, is it this one? No. Maybe not. What is it called? I've got it on the slide there. Ay, ay, ay. Okay, it's called this. Give me a second. Okay. Yeah, okay. So this is the video, and I talked about the work from 1950s, published in 1963. About how you could make superconductivity by taking a piezoelectric material and coating it on the surface of aluminium. And this was before the Salvatore Pais patents. That was my hunch. And then if we go to around about here. Some videos. Here we go. So this is a short arc tube. I'll put it over here because I'll give a nice contrast. And this is the sort of thing that you might have in a projector for a cinema projector, and it produces an incredibly bright white light. And you have your cathode here and your anode, so it's kind of like a Shoulders charge cluster generator, but without the wetted cathode and so forth. But I don't think he was using this as a light bulb. He was just using it as a means to create charge discharges, and those could be creating EVOs and scalar waves that are able to go into the environment. So you will see him using this. Whether that's particularly necessary, don't know, but it's here as well. It's something else to consider.
I'm going to put that over there just for safety reasons.
So there we go, and essentially, John will say this is very, very important. And why would he say that? Well, let's go back to our presentation here. So, not that. That isn't our presentation. This is our presentation. So basically, he was saying that he used that. Right, so in 1992, Solin published a patent, which I didn't come across until August 2020. And in that patent, which showed all of the things that we had been sharing from very many different experiments, he claimed that when the electron beam goes into the low vapor pressure metal, the electron clusters formed into two soliton types, which are of opposite magnetic charges, and that these can then cluster and form cylinders and spheres, a bit like our channels in our Vega Valley, almost certainly exactly like that. And when they form these clusters, they produce coherent light. Okay, coherent light. And typically that will be very, very high intensity light. Now, I'm going to show you a video from just the other day. In fact, it was 2 and a bit weeks ago by Anatoly Klimov. And there's a very, very important couple of slides in there. In fact, I can either show you that, or I can show you... Oh, what am I going to show you? Am I going to show you that? Maybe I'll show you that, yeah. Give me a second, I'll just find it. Yeah. Yes. Okay, so you can go and have a look at this on the MFMP's YouTube channel, but this is one of his experiments. This is the plasmoid here, and he uses an X123, which is an X-ray spectrometer, and he observed that depending on how much he does his high frequency, high voltage discharge into the reactor, you get first low spectrum emissions here, and then it gets higher and higher energy spectrum. These are emission lines of transmutation of elements, and then you get a coherent sheath that whatever is going on inside is masked, because you get what Matsumoto said in his 1995 paper, a smooth curvature of photon emissions. And if we look at that, depending on the time, you start with the discharge and then you get these other elements. So you can actually create different outputs in terms of photon energies depending on your management, your control of the system. And you can see the optical spectrum output here. And here is the most important thing I think we need to say, is he said that when you had the nanoclusters forming, the exotic vacuum objects forming, the UV emissions went up 1 million times. 1 million times! So let me just find the exact sentence where he is saying that. So give me a second. For you. Okay. I think it's here. Nope, it's not there. Nearly there. Yeah, this will all start to make a lot of sense soon. You'll be pleased to know. Talk amongst yourselves. Okay, I might just have to dig it on YouTube. I can't find it immediately here. Unless it's that one. No, I'll find it on YouTube. Ay, ay, ay. Okay, so I'm going to try and play this from YouTube. So let me see if I can do this without it causing me a nightmare. This is very, very, very important. What I managed to scrape out of Anatoly Klimov. So I think it's somewhere here. Okay, yeah.
You obtain this value, COP.
Humour, if you will, humour me, the last one, the comparison of the any transmutation compared to Slobodan Stankovic's work. You were talking about the sodium. Okay, so it's here. Yeah, did you have a spectrometer for looking in the UV spectrum, Anatoly?
UV spectrum, I have no such type of the spectrometer because of our optical spectrometer. The minimal wavelength resolution higher than 250 nanometers.
I have the same problem, and in fact, it's no good really below sort of 350. And I wonder if you're having the same problem. You look like you have a cutoff around about 300. So probably it would be very useful if you could acquire such a spectrometer and rerun the experiments, because I think this UV spectrum is a very important range.
Concerning your question, we measure the ultraviolet radiation near the 200 nanometers using the apparatus function. And it was very interesting results in the ultraviolet range because of the increase of the ultraviolet radiation amplitude was the factor 1 million times higher than the initial factor with the plasma without nanoclusters. When we use nanoclusters, amplitude of ultraviolet is unusual high, extremely high.
Is it 10 to the 6 or 10 to the 7?
10 power 6.
Okay. Okay, so there you go. That is just over 2 weeks ago that presentation was put out. And I could see that there was something very interesting going on in his work, and I wanted to dig into what I believed he would see, which was this intense UV production. And he said, yes, when without nanoclusters there, we don't see the UV, very, very little UV. But when the nanoclusters are formed, the charge clusters, the exotic vacuum objects, the micro ball lightning, the ball lightning, the UV detected goes up 1 million times. 1 million times. Okay, hold that in mind. Whilst we're on this presentation of Anatoly Klimov, he also showed here, he did, honest, if I can show you the slide, not in this one, in the other one, here. He showed, so you see the chamber here. These are plasmoid tracks on the inside of the fused quartz. So obviously he's doing very, very intense discharge. It's very disruptive. And so he's getting these these EVOs eating the quartz here. And this is similar to the things that we've observed in other experiments like Lion and such. Okay, so that just hold that in mind also. I don't think we need that one anymore. Okay. So that was Anatoly Klimov. When clusters form, the UV output goes up 1 million times. Okay, so Ken Shoulders, he preferred to use xenon to stabilize his exotic vacuum objects, as the gas is both heavy and easily ionized. Why is it easily ionized? It is easily ionized because it's a very large atom. So the first ionization energy of the noble gases is the lowest other than radon, but radon's radioactive, so you don't want that. So xenon is the most desirable gas that you could choose for the ionization level, and also because of the mass. It's very good at stabilizing the exotic vacuum objects. It can be made to fission, or if it can be made to fission, it can release vast amounts of kinetic energy. So let's say you only had a one fission in a blue moon in your reactor. Your xenon, let's say 124 here, would fission to cobalt and nickel, and you would get 41.31 million volts, electron volts, in the cobalt and nickel kinetic ejections of that fission process. So the kinetic ejections of that fission process. And so you can imagine that when the charge clusters, the exotic vacuum objects in the line core were disheveled, at that point you got some kinetics of synthesized elements coming out, instantly heating the material, but then the overall mass of nucleons and electrons wants to gather its thermal and kinetic energy back to reconstitute normal atoms, and that causes this intense drop in temperature. So you have a little burst, and then you have a boom through the floor. So we've got the reaction here. Nanosoft.co.nz, the Philip Power and myself produced a reaction calculator based on Alexander Parkhomov's reaction tables, and you put in E equals xenon or an order by MeV, and you see, I don't know, whatever it is about in the tens. I don't think it's in the hundreds of reactions. Now, Ken Shoulders said very, very, very clearly that exotic vacuum objects produce UVs and soft X-rays. Now, I'm now going to go to the presentation of Alexander Shishkin, because that is very important for our discussion here now. So I think I've got it in here. If I can, I find it. New type of penetrating radiation. There we go. So this is called a new type of penetrating radiation. I've spoken about this before. And in here, you have the fact that Charles Glover Barkla, who got the Nobel Prize for discovering characteristic X-rays in 1917. He spent the last 33 or something years of his life, basically the rest of his life, trying to work out what the J phenomenon or J radiation was. And this, it would, according to Shishkin, and I agree with him, this was actually exotic vacuum objects that he was observing. And so basically, there we go. So electromagnetic radiation, including X-ray and gamma radiation. These are the normal forms of radiation. Radiation in the forms of fast particles, but what Shishkin is talking about is a new form of radiation. And these are other people that were looking for this at the time. And then this is Martin Fleischmann with Christopher P. Tinsley talking about this kind of radiation here that goes from over 100 keV up to 120 keV. Gozzi observed it. I think Preparata observed it here. Preparata here, and so forth. And this is this J radiation, and this is more Crowther replicating this work. And here we go. This is Martin Fleischmann. Well, it's soft X-rays, but soft X-rays would never get out of the cells. Here we go. We've got soft X-rays being reported by Fleischmann in Preparata and Stanislav Spack and so on. So this is something that is produced in these experiments. Why is it produced? It is because of exotic vacuum objects, in my view. And here, for example, photo 1 shows traces of explosive unpacking of energy solitons, each of which contains more than 10 to the 11 electrons and at least 10 to the 5 ions established by Ken Shoulders. During the explosion of such a soliton, a significant part of the electrons acquire kinetic energy up to 6 to 10 keV. So these are called hard X-rays. 10 killer electron volts, 10,000 electron volts. Hold that in mind when one of these structures blows up. You get 10,000 electron volts. Therefore, characteristic mechanical damage of the film in the form of an umbrella and or birdie appears. And so that is what we've talked about a lot. And that are these structures here, which are, in theory, condensed cold neutrinos. And that's why they're neutral, but they're containing electrons. And so their charge is screened until they blow up. And it contains ions. And he established that the ions could make pits in material that had a certain depth and width, depending on the material that they were traveling through. So here we go. So that is Alexander Shishkin talking about Shoulders, talking about these things that are the same. And I will now go back to the main presentation. And what did I needed to put something in there. What was I going to put in? Oh, God, I think I'm going to miss something, which is really, really rather important. Anyway. Okay. I'm going to go ahead anyway. I can't remember what it was right now, so just have to do it out. Right. Okay, so Ken Shoulders EVOs produce UV and soft X-rays. What is deep UV? Well, deep UV, according to Wikipedia here, is 100 to 280 nanometers. Okay. What are soft X-rays? Well, we've talked about them. They are normally 0 to 5 keV. They're soft X-rays, and it should be in here. So I think it's in this block here. Okay. This is where I might get a bit messy. Oh dear. Now what have I done? Don't go away. Okay, give me a second. Right. What I was trying to do was this. Okay, so soft X-rays here. You can see, maybe if I zoom in a little. Where has it got? Is it going to give me soft X-rays? Oh, now I made it too big. I can't see where I am. So X-rays with high photon energies above 5 to 10 keV. And so notice that Shishkin was saying that you get 6 to 10 keV when these charge clusters, these solitons, blow up. So they would be hard X-rays, and they're so-called hard X-rays, whilst those with lower energy and longer wavelength are called soft X-rays. Okay, so it produces predominantly soft X-rays when they are cohering. Okay, but when and UV, and when they blow up, they produce hard X-rays. Okay, so there's that. Right, now I need to go back to the presentation I just showed you. No. Give me a second. Okay. So from Glowstick 5.2, I think in 2016, beginning of 2016, late 2015 to 2016, we saw Spectrum 7. In fact, it was Echo, the cloud researcher, who observed this in the middle of the night and pointed it out to us. And Bob Higgins analyzed this and found that most of the measured samples, 93.98%, were below 255 killer electron volts. So you can see the fall off here, but the vast majority of them actually are in this low energy area up to the sort of 200 and something, 150 or whatever, that was talked about by Stanislav SPAC and by Preparata and by Martin Fleischmann and by the likes of Charles Glover Barkla and so forth. And so this, in my view, would be a large exotic vacuum object that is blowing up. Now, in the work again of Klimov, he is, again, if you look here, the majority of his X-rays are below 255. So you can see the 255 here. So the vast majority, nearly every one of them, is below 255 kV. So that is a consistent observation with our observations. But of course, there are some energy that is above there. Okay, so that is the consistent observations between blowing up of these structures. So you get higher energy ones when you blow up the exotic vacuum object structures that are being formed. So I'll go back to the main presentation, and we're going to get to the money shots about how this actually is going, how the so I believe that he is achieving what he claims he's achieving, but maybe not knowing how it works. I've tried to help where I can. I've seen his paper change a few times, but anyway, you can lead a horse to water. Right, okay. So I have here two slides. One is I've just showed you the Glowstick 5.2 signal and the Klimov plasmoid. Right, so the question is, what is the first ionization energy of xenon? Okay, well, I'm going to pull up a slide here, a website rather, where you can go and see ionization energies. And this was all going to be part of something electric part 2. You know, many of the things that I'm talking about here. But again, it had to be delayed because I didn't have time, and I really wanted Rossi to just come out and just say how his thing really works. I wanted him to know how it really works and to tell us how it really works. I didn't want to have to tell him how his thing works, because then he could just pretend that that's how it works. Anyway, he's not far off, actually. Anyway, he just had 3 Klimoffs and mostly the work of Ken Shoulders, to be honest. The Lockheed Martin patent was helpful. But anyway, this is P table, and I've got here selected the ionization first energy down here, and I can switch this to electron volts. Okay. Now, if anyone knows anything, they will know that the element in the periodic table that has the lowest ionization energy is cesium. So its work function is very, very low. Now, you'll see this is 3.894 electron volts. And you'll see that potassium, which I chose for the EVO Blaster video, which is readily available, because you can get all potassium hydroxide from your hardware store, this is 4.341. So this is one of the best that exists. Rubidium's a little bit harder to get, francium's harder to get, but cesium is your best. But, as I said, as of the noble gases, look at the energies that you require to ionize these different things. Hydrogen is 13.598. Helium is 24.587. Neon drops all the way down to 21.565. Argon all the way down to 15.760. This is the gas that we're mostly using in our Vega experiment. So 15.760. Now krypton, and by the way, we're going to be buying some Xenon. It was meant to be bought earlier in the year, but we didn't have the money. So anyway, we're going to be buying some Xenon. It's like 1,500 quid for a bottle, but we probably won't have to after this, and you'll probably know why. Anyway. So krypton is 14 EV, but xenon is 12.13 EV. Now, of course, I said radon is lower, and it is. It's 10.75 EV, but it's radioactive, and we don't want that. So xenon is heavy, and it is stable, and it is 12.13. Now, that is quite a lot more than cesium, but cesium is very volatile and very difficult to deal with. And potassium is less of those things. That's why it was chosen for VEGA-EVO Blaster. But it's not a gas, is it? So it's less easy to capture into a swirling soliton of electrons that is producing intense magnetic fields and electric charge separation. So xenon is the thing, and this is why it was used by Ken Shoulders. There's a logic to, a method to his madness, as you might say. So there we go, 12.13 EVs. Now, how do we get that energy? How do we get something to cause that ionization level? Okay, let's go and find out. We will go to a different table here. And I'm going to copy that, and I'm going to go here. Give me a second. So, here, we've got a little thing here called photon energy. And we want to change this down here to electron volts, okay? And we want to type in here our 12.13 electron volts, and we want to change this to nanometers to find out what the frequency of light is. We need 102.2133. What is that? What is that? That, my friends, is deep UV. It's deep UV. 12.13 electron volts. So, what did we say? That's 102.2133. What did we say the deep UV is? 100 to 280. Soft X-rays. So we know that 100 is sufficiently high enough to ionize the xenon. But if we've got 0 to 5 keV soft X-rays, and we know we get these because we observed them in line, Ken Shoulders is saying they're there, and so on, and ad infinitum. 5 kilo electron volts, that's a lot more than what we need. It's a lot more than what we need. And then if we get some harder X-rays or other types of soft X-rays, typically in this range, we've got 280 to 530 EVs. What I'm saying is the energy that is in the photons that comes out of the forming of the coherent matter in an exotic vacuum object and larger charge clusters is very, 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 very much more significant than is required to strip an electron, producing an ion and a free electron, from xenon. It's going to be a lot harder if you're using krypton or argon, but xenon, you get a heavy atom and you get electrons, and the electrons will be free. They're in their plasma. So you are doing kind of what I was doing with the potassium hydroxide, causing the inverse beta decay, shooting out a 1.551 mega electron volt beta particle. The beta particle ionizes a whole bunch of whatever gas is in there. In the case of our experiments, that would be mostly nitrogen. And that is free electrons that then can move to the anode and produce excitation, which will condense in the exotic vacuum objects, producing more intense solitons, which will do more work with the potassium-40, producing more of the things coming out, and you get a virtuous cycle. In this case, you are getting ionization of, and I can talk to my conclusion here. If you drive exotic vacuum objects, they will produce a lot of UV. Klimov is saying 1 million times more. Okay, when the plasmoids are formed, the charge clusters are formed. If you drive them harder, they will produce soft X-rays. And in fact, they're producing soft X-rays for quite a period afterwards, because we know from Klimov, and we know from the experiment that we did in 2017 in the plasma flow equivalent discharge system of Suhas Ralkar in India, that there's voltage coming out of a piece of metal. And in Klimov's case, he's seeing the plasmoids running around on the surface, and those plasmoids are emitting. They're glowing. Why are they glowing? They're glowing because they're ionizing the matter around them. Whether that's the gas, or it's going to be the gas, it's going to be in air, whatever. And so they are ionizing the gas. You're getting a glow because it is cohering matter and producing these soft X-rays. And we know from the line X-ray film that X-rays are being emitted, or at least fast electrons, or plasma, a magnetic flux tube with electrons moving through them. Something is causing those X-rays to be exposed. Just like the X-rays are exposed with the work of Alexander Shishkin. Okay, so I'm saying here, and up to 10 keV, according to Alexander Shishkin, in a new kind of penetrating radiation that we went through. They can produce on detonation, in our experiments, and in Anatoly Klimov's experience, up to 250, the majority of them, even higher, but most of them, up to 255 keV. And if you look at Matsumoto's 1995 paper, he's claiming something similar in this respect. This will massively ionize xenon, producing a lot of free electrons that then can be condensed and releasing more photons. So you have a virtuous cycle. Now, what does this mean? This means that depending on how you drive a system like John Hutchison was using for much of his time, and in fact, that tube was the tube that was used, as far as I understand it, in experiments in the early 2000s that produced the samples that we all know so well, like the coral twist. And this sample, where we apparently have derived the structure of the exotic vacuum object, the similar structure here, this one was also produced with that particular xenon intense HID lamp. It's the sort you would use for a projector, that one. But, you could have ones for military searchlights on ships as well, which would be even probably bigger. But that's one for a projector. But you don't need to get them that big, and we'll look at something. And so, depending on what you do, you can produce heat. Xenon lamps get really hot, but if you drive an exotic vacuum object through a stimulation regime, so that you're mostly condensing the clusters. Now, what do you need to do? Well, rather than having a continuous discharge, you need a pulsed, which is intense. And therefore, you're hitting the Tibetan singing bowl. You're going bang, like that. There's two ways you can do it. You can resonantly get there, or you can hit it. And so these are two ways that you can achieve the production of the charge clusters and force them into the coherent state. The more coherent they get, you move them, the more you will shift through from the visible spectrum into the UV, which will be able to further ionize the xenon, through into the soft X-rays, which will massively ionize the xenon. And you will get bluer and bluer light as you do that. And you will go from thermal photons to cold photons, and cold photons which can produce electrons. Because not only are you going to produce electrons that feed the exotic vacuum object, you're going to produce electrons and become a current source. You're going to become a current source. And then if you get it right, when you break up that cluster, it's going to want electrons back, like it did in our Lion experiment. Okay? It grabbed the electrons back to reconstitute the atoms. And so that, if you put a diode in there somewhere, you can pump the electrons out one way and you can suck them back in the other way. Pump them out that way, suck them back in the other way. Pump them out that way, suck them out this way. So you have a method where, by controlling this system, you can create heat, light, and electricity. Heat, thermal photons. Light, visible, and UV, which could be downsampled using lanthanide oxide and various other phosphors, like you have on a cathode ray tube, like you have in a strip light, where they have a mercury vapor which produces two intense UV bands, which are not good for you, but you can use normal phosphors commercially available and convert those into the visible spectrum. So 1,000,000 times more UV coming out of your exotic vacuum object, as observed by Anatoly Klimov. You take that 1,000,000 times UV and you convert that incredible amount of photonic energy into excited phosphors that produce a lot of light. A lot of light. Yeah? We already know that your compact fluorescence can be really, really efficient. Now imagine that you're not just trying to excite electrons to do a bit of that and I think the band of let's have a look actually at the mercury UV band. Mercury UV. It's a low pressure, like the one I have in the other room, which I'm not going to turn on. And we're going to use that for experiments, that pre-war low pressure mercury lamp. Mercury lamp. Okay, so this is mercury vapor lamp. You see, this is the sort of color I had out of my low pressure mercury vapor lamp. This is a classic sort of indoor lighting one. Wouldn't want to be that near that. Not with my eyes. You'd end up with cataracts. Right, so here we go. Look at this. Look at this. This mercury lamp right here is below the 202 or whatever it was. If I zoom into that. The 200, was it 202? Something like that, 202. 184, this is a big band. So the photon energy it needs is 102. No, it's not enough. It's 184. So Mercury can't do it. Mercury can't do it. But we know that exotic vacuum objects can produce X-rays. Matsumoto saw it. These high energy, these photons coming out, the X-ray energy. Preparata saw it. Barkla saw it in the 1910s. Barkla saw it in the 1910s, and many people that work with him. Okay, Martin Fleischmann saw it. Preparata saw it. Stanislav Spak saw it. Okay, so these energy of photons will come out. They will come out of your exotic vacuum objects. Okay, so where am I going with this? Okay. So now, what was the coup when everyone was going, oh no, what a terrible demonstration? I was going, but look at the blue light. What a terrible! Look at the blue light. It looks a lot like something that's going to be producing a lot of UV. Okay, and I think that's going to be an exotic vacuum object in there. And then I have to thank Can again. Can has done something today, and I'm going to find it because it's really rather special. And we'll find it. And then I might have to switch computers because I've got a load of links on the other computer. Okay. La 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 la. Right, I'm going to switch computers because I've got everything already on the other computer. So just give me a second. I will have a look and see if I can get it. Oh, I probably shouldn't have done that. My computer's going to complain it's been taken away from loads of other. Okay, let's see if this computer's not going to blow up on me. Okay. Give me a second. Hopefully we will have what we need. Without things dying. This could take a while, because it just does on this computer. That was predictable. Any questions? Yeah, it probably is now obvious why I'm so interested in light bulbs. And Tesla's light bulb, which produced a lot of UV and X-rays. Why? Because it was making charge clusters in the 1890s, 1891, 1892, right? And that is taking even longer than I thought it was going to take. Typical. Right, okay, maybe we can do it like this. Okay, nearly there. Okay, right. So Can turned on his sleuthing skills, and he found that several of the items in the presentation were off-the-shelf items, like this converter, regulator, 36, 24, 12 volts down to 5 volts, so it might be used for control circuitry. And there's another shot of this same device. This one is a DC boost converter. So this is stepping up from 3 to 35 volts to 5 volts to 45 volts. So this might be taking the power back from the device and powering the device here. So these are standard off-the-shelf components. But the interesting thing was he found this, which is a xenon ballast. This was the unit which had the top taken off it. And this was driving the thing. Now, this is another Xenon ballast. This is a 100-watt one, and the one that looks similar to the one he had was a 35-watt one, I think. 35 watts, is it? Something like that. It says down here. And given the fact that we should expect a huge energy gain from the process, now, here's the important thing. This may not be a nuclear process. It may not be a nuclear process. It's basically rectifying thermal and kinetic energy of electrons. So thermal energy for the environment. But I predict it will be a condensation process of not only matter, but also matter that you normally aren't able to interact with. That be the cold neutrinos, flux, which will be able to be condensed into those exotic vacuum object structures and provide additional energy, kinetic energy, to electrons that are emitted by some of the photons that are emitted, and that can provide extra current. And also there will be some transmutation of the xenon, but it doesn't really need to be much, and that comes down to how you would control it. So depending on how it's controlled, you will get some condensation of material, which will produce ionization, which can then be rectified, as I've described, as you build and break up the charge clusters. You can get transmutation of the xenon, that's the available gas in there, and possibly any electrode material that's in there as well. And you can get condensation of relic neutrino condensate, well, it is a condensate, but anyway, more further condensation of that condensate, and harnessing of the embedded energy in that. And you will be able to get full-on transmutation. I might have said that already, but anyway. So here, this is the Xenon ballast. You can get other ones. This is 100 watts, and this is interesting because that is essentially what is claimed for the output of the device. But I think probably using this one here, which does 35 watts. I think if we go here, yeah, it's got 35 watts there. You can see it. I believe you could probably achieve it with that. And it's a high intensity discharge tube, and it's one of these. It's a light bulb. And you know what? I think you're probably looking at exactly one of these units, and you can actually buy kits. And you could imagine that this is the, whatever it is, this one's, is it a 35 watt one, this one? This is for a Porsche. Doesn't say, does it say? 12 volt. Plus and minus, 35 watt, there you go, in Russian, there you go. That's Russian for watt, BT, okay? And it's for driving high intensity discharge xenon. So this is a kit, and you can imagine this light bulb is in that square box, pointing downwards. And what you've effectively got there, my friends, is a miniature version of the one that John Hutchison was using. And it's got xenon in there, and it's got a cathode and an anode. And it's got the little bubble. It's literally a miniature version of the big one that John Hutchison was using to create the samples that I have been studying over the last several years. And that's it. You can mass produce these because you don't actually have to make the useful bits. You just go and buy it off the shelf. And it's square, and you can put a bit of plastic around that. And as long as you know you're running it cold, because you want to be focusing on producing electrons, and you can do it. So that's it, really. There are all types of other HID bulbs. Here's like a mid-scale version of something you can see here. This is sort of like what you saw, but it's basically a Ken Shoulders Evo generator. You just need a different regime. Yeah, here's another one. It's like you can get one of these bulbs here for 289 crowns. I mean, what is that in real money? That is about $10, a little less than $10. But you can get smaller ones. What else have we got here? These are, you can get phosphors here from this company, Phosphor Technology, to convert X-rays. This is X-ray phosphors. X-ray phosphors to convert the X-rays into various colors: green, red, blue, white, blue, yellow, white. What do you want? What do you want it? And you can see these are lanthanide oxides. So this is gadolinium oxide with sulfur. This is gadolinium oxide, praseodymium, cerium, and fluorine. This is lanthanum oxide, sulfur, and europium. Lanthanum oxide, sulfur, and terbium. And this one is actually zinc, cadmium, sulfur, and silver. Obviously, silver is good at down converting light from UV. You can imagine a company that would create very, very good EVOs from discharging capacitor banks, maybe supercapacitors, into, maybe they would use liquid metal like was in Tesla's death ray in the 1930s, or in the patents of Ken Shoulders for his exotic vacuum objects from the 1980s. And you would use, silver, because that it would be very good at down converting UV. You could use that. You could. Yeah, you could. And here you can use perovskite, and I mentioned this many years ago about converting the output from these reactions into usable energy, and you would have ideally down convert to improve your solar cell performance. So that is essentially it. It's very clear, in my view, how to achieve this. And everything you really needed to know was in EVO Blaster from 1 year ago today. And the video that I shared on, I talked about it before then, but the video that I shared on January the 7th, 2018, but I discussed it from about March publicly, 2017, Ken Shoulders worked. And really taking the PNTele Project Fedora work, the Echo work, the Lion work, and the Vega work, combining that with John Hutchison's use of a high-intensity discharge xenon bulb, the learning from Solin 1992 patent, the fact that Anatoly Klimov has very clearly determined that the UV output when charged clusters of forms goes up 1 million times, and the observations by many authors such as Alexander Shishkin and Matsumoto and Ken Shoulders specifically, that they produce UV and soft X-rays, and these are things that we've observed in terms of soft X-rays from Lion reactors, that deep UV is sufficient energy at 100 nanometers to produce ionization of xenon, and certainly soft X-rays up to 5,000, 5 keV is more than enough to do a lot of ionization. We know we get higher than that from a blowing up exotic vacuum object from glowstick 5.2 signal, and we know that we get it from Klimov's plasmoids, and given the first ionization energy of 12.130 electron volts and the 102 nanometer light of that, we have a result that we have a system that may not actually be using low energy nuclear reactions, but likely there is some going on, and it can produce heat, light, and electricity, and it's based on your stimulation. And it comes down to doing what Ken Shoulders and John Hutchison were doing, which is creating EVOs in a xenon discharge tube and just controlling the regime, and that's it. That's it. That's all it is. It's that simple, and there's nothing you can patent. So I don't know what people think about this. But I've got this idea where potentially we could run a competition, and we could do something that I saw and I was quite amused about at the beginning of the internet, and it was called the 1 million pixel website. And it was basically a website, and all it was 1 million pixels, basically 1,000 by 1,000 pixels. That's it. That's all it had on there. And you had the option to buy a number of pixels for $1. And so that's $1 million. And so could we run a competition where people buy an advertising space on this one single page, and they pay $1 per pixel, and it'll be blown up to the whole page, so it's only 1,000 pixels by 1,000 pixels, so you work out your image. And then the first person to produce a working light, heat, and electricity device based on this understanding, and produce the full schematics, gets whatever the prize fund is at the time that it's determined that it works. Okay, so you have to produce the device, you have to do the testing, and then you have to hand it over, and you get whatever the prize fund is. And I'm going to go out on a limb here. If I can raise a sensible amount of money using the Kickstarter for the Vega Valley, I'm going to speak to Henk about this, and if he's okay with it, I would be happy to buy the first 1,000 pixels for $1 a piece, and have that on there with just the MFNP maybe in the middle or something. I don't know what people think, but you know, it would be just a bit of fun. Anyone could buy some advertising space on this one page, and I can host it somewhere. That's fine. And the prize fund can be noted down the bottom. And what I would consider doing is setting up a very specific Bitcoin or other cryptocurrency account, and therefore people could use the blockchain to confirm that the currency is in there and it hasn't moved. And so when people buy the advertising space, it's effectively held in escrow in this Bitcoin account, and people can go and look at the hash code and see that the prize fund is in there. That's it. That is my concept for this. So if people think that's an interesting idea, I think we have enough. You can go out and buy simple control equipment, try different parameter regimes. You know kind of what you should be doing with all the study we've done. You can look at Ken Shoulder's work. You know you might want a bit of a disruptive discharge. There's many ways to achieve that. And then you want to create the clusters, make and break. As I said at the beginning of 2017, you need to make and break these. You could make them up to a certain point, but you're going to probably want to break them. So there's going to need to be some buffering in there. It doesn't matter if you just want to produce heat, I guess, but you know, different control regimes produce thermal photons, produce cold photons, which can stimulate the production of more electrons and light. If you're going to be producing a lot of UV, you could then have a system where you have something to down convert that light, so you can create the range of things here. And it will do transmutation, but of course you want to try and avoid that, because you want to be creating what do you call it? You want to be having a stable system. And I would ask that everyone is happy with us also making this offer open to Andrea Rossi, right? So that if he wants whatever the fund is, which is going to potentially get up to $1 million, if he can just provide us with a schematic of how the thing works and provide us with a device to prove that it does what it says on the tin, he will get the prize fund. I don't care who it is. I don't think anyone should care. I just care that this gets out before people that think they know what they're doing die. This is a real thing, my friends. The evidence is there since Barclay discovered J radiation in the early 1910s. It's there. Shoulders demonstrated. Lyon demonstrated. Klimov has demonstrated. Hutchison has demonstrated. We've demonstrated in Vega. Dave and Henk, we've demonstrated absolutely conclusively we can create coherent matter. This is the underlying process that you need to do it. Matsumoto observed, obviously. The US Navy, the US Air Force have both said ball lightning is the way forward. From that 1993, published in May 1995 paper. They are agreeing. This is a way to target the energy output. This is. I just wish Rossi could have said it. I've been waiting for this presentation now for over 2 years. And going, please, just tell people how it works. Just tell people how it works. Don't fiddle around and with a couple of multimeters and some other person just doing some questionable reports, which may actually be accurate. They may be accurate. You just can't tell from looking at the presentation. Anyway. So, right, so if anyone has any questions now, this is the time to ask them. I've been wanting to do this for a very long time. It's been so depressing to have watch the demo being rolled into the future, rolled into the future, rolled into the future. And it's like, stop it already. So adjusting the pulse rate, watching. Okay, so Stephen Halls asks, Bob, can you elaborate on the idea of adjusting the pulse rate, watching light get bluer and the temperature cooler until equilibrium? Right, well, basically, once you've formed an EVO, it may not be in a fully coherent state, and you need to resonantly pump that. so that it becomes coherent. And Ken Shoulders is very clear: you feed it electrons, you keep feeding electrons. If you don't keep feeding electrons, it actually may become neutral. In fact, you need to keep it non-neutral until you blow it up. Otherwise, it's then going to go out as strange radiation, because it'll just be condensed cold neutrinos carrying some masked electrons and some ions, and they do bad stuff to things. And they won't be detected by any of the radiation detectors used by Rossi in his presentation yesterday. None of them. It won't work. No, not work. So, very disappointing with the radiation monitoring there for the device. Now, like I say, and I said this in 2017 on Steam, I said you need to build, make and break. You can't drive this too hard. So there will be an optimum regime of resonant pumping. And this is what you'll need. It's just, it's now possible. The most important thing ever in developing a technology is just to know it's possible. If you're told all of your life that you can't have heavier than air flight, you just accept it. It takes someone to say, this is definitely possible. It's definitely possible. And when you've seen that thing in the air, you go, well, it's in the air. It's in the air. And you have data going back to Barkla from the 1910s. And it's all consistent. It's all telling this same story, right the way back to what was shared just over 2 weeks ago by Anatoly Klimov. Defined, understood, already supporting what other people have claimed. What you've got here is you're using. This is why I was talking about in the beginning of late 2017. What goes up must come down. What goes up must come down. It's rectification. You can use this technology to do propulsion by mass rectification. Shoulders wrote a paper on that in the publication that we are making publication of Takaaki Matsumoto. It's in there from, I think, 1996, 7. He's saying you can make these itonic clusters and move them into a place and then blow them up, and they'll provide an impulse energy. So you've got impulse and you've got mass rectification. 2 ways to do this, other than the one that I talked about in the APEC presentation. Okay, so a lot of the times what you're doing is you're doing rectification. What I've described tonight is a process by which, and it's just so good to get it out of my head, so I don't have to think about it again, really. I will do better presentations than this. I'm super sleepy and I made it in a couple of hours on the fly. But it's so good to get this out of my head. Having seen that video that I published a year ago today from Henk's experiment, delivered everything I could have possibly imagined. You can't imagine how excited I was when I saw that. And I will, and I've actually been discussing this with Alexander Shishkin this week. He's given me permission to share his latest work. I might discuss that on Sunday, but he's observed the same things in different ways. And so I've been trying to speak to Alexander Shishkin for ever since 2018, and he reached out to me after my last Russian presentation. So absolutely stoked. The reason I was so unprepared tonight was I was basically talking to him all day. But anyway, this works. It just works, and it's energy rectification. You can think of it almost like a heat pump, where you've got a system of electrical power that's taking thermal energy from, I don't know, an underground heat source like water aquifer or something, or from an air source, and pumping that into your house and doing the vice versa, the heat to the outside when you're in the summer or something. So it's kind of like a heat pump, and in fact it'll do that. Like I say, this system will capture heat from the far field. So if you've lost that heat in driving electrons, ionizing the electrons, and they've gone through your system and it needs to grab that heat back. In part of your cycle, you're going to be grabbing heat. It may actually be the case that the device actually runs quite a lot colder than ambient air. And it's rectifying that heat in a way which is just, you ordinarily wouldn't expect it can do that. But we've seen it in this. And you've seen it in EVO Blaster. You've literally seen what it's doing right there in that video from a year ago today. And so heat, light and electricity. Well, on our website from, I think it was October the 12th, 2000 and, no, somewhere around it in the third quarter of 2012, we called this the new fire. You can see it in our goals, and I think we're there. If you had a rotating anode, e.g. a rotating liquid, and rotate the EVO on its surface to a different place where the magnetic effects could move it into the wire. And maybe, Stephen, but I think, I don't think we need to overcomplicate this. If you can have a system that is largely solid state, other than the small amount of plasma in the reactor, and you can produce heat, light and electricity without overly complicated. The thing is with an EVO, if you produce instability with a, like I was saying earlier, the reason you're seeing the explosion on the cathode with the exotic vacuum object there is because you're going through a impedance change, and so you want to keep the plasmoid in between those gaps, right, for as long as you can in the cohering matter state. So where it's producing photons of a high enough energy to ionize the xenon. That produces free electrons which can be utilized and also keep the process going with an apparent gain in a non-chemical way. You don't want to overcomplicate this. Basically, if you get an EVO which is coherent at any point, it will destroy your reactor. And if you get it so that it's moving around, like I showed you on Anatoly Klimov's work from just over 2 weeks ago, if the plasmoid goes out and it touches fused quartz, which normally melts at 1700 degrees C, which is, by the way, what those HID lamps will have as a enclosure for the xenon, it'll eat a hole through it. It'll just eat a hole through it. And then you've lost your xenon gas, so the game over. When you break this thing, it will not work again. And the only way you could know what's in it when you broke it is to have a residual mass gas analyzer there right when you broke it. So this will not work if you open these things up. Is this worth the Nobel? Not if you don't talk about it. We've been giving him a chance since 2017. Since 2017 to explain what this does and how it does it. Ego and protectionism. I couldn't risk any more time. I was happy that his voice was stronger, but he has had cancer. And I can't risk that he dies and something happens to me. I can't risk that. So I hung out and 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 I told those people that wanted me to talk about what this means and why haven't you done, and people know that who I'm talking about. Why haven't you spoken about something electric part 2? And I said, well, you know, I need to see if Rossi's going to do it. I need to see. But I can't take the risk. You have no idea the mental torture I went through in March to April last year when I had COVID. You cannot even begin to imagine. I thought, I'm going to be that person that I'm saying goes to the grave with information that they absolutely should have shared. I don't want to be that person. I was horrified. I was sitting there lying down and going, I might die. I might die. And then what has it all been for? What was the point? What is the point if you don't share it? Why did you bother learning it? What? Just so you could go, oh, I know something you don't. Shut up. I'm sorry, Andrea, if you listen to this, you had 10 years. Lots of people have wasted a lot of time. I wasted a huge amount of time. But, you know, you could have said how this works, not with some sort of, oh, it has a terribly complex AI system and you know, it's some magic gas in there and you won't know what it is and my patent covers it, and like, no, it doesn't. It's basically a plasma focus device of Ken Shoulders. Using publicly announced things by John Hutchison and the stuff that's already in the public domain. You just have to join the dots, make the whole round thing. Yeah, so Gordon, the safety profile needs to be understood. But if you, as I said in 2017, make break, so that you don't get the Evo too intense, you're in a better way. But regardless, you will be able to make devices that you could put underground and you'll be able to produce your heat, your light and your electricity. You just pipe it, yeah? And the strange radiation has an amount of distance it can go through, and you'll be able to work that out. And the Russians have done fantastic work on this. So, you know, it's within our grasp. It's within our grasp. We are really at the dawn of an old age. Best thing for strange radiation protection? Well, I'll quote Alexander Parkhomov. Distance. Dilution is the solution to pollution. Inverse square law. Get away from it. So Andrew, we're driving the Xenon bulb terminals with TBD optimum waveform. Yeah, to be determined, yeah, but here's the thing. I think if there's a prize fund on the table, and like I say, I'm willing to shove up pay for the first 1,000 pixels straight off the bat, because you know, in long term it'll probably save me many thousands of pounds in heating bills and lighting bills and all of this nonsense about global warming and all the restrictions and the carbon taxes and the social credit stores. None of that will be a reason to be. It'll have no reason to be if we can get this out the door. It won't have a reason to be. And it has to come from the people. It's not going to come from a person. It has to come from the people, right? The evidence is all there. We can now do it. We can do it. You have to believe it. You have to believe it. I need a beer. That sounds great, Corky. That sounds great. We are meeting on Zoom. Well, I'd like to join you, but not if it's too late. In fact, it's too late for me now because I've got to be up in the morning. We're going sledging. Lots of snow here. Have to get past the pseudoscience claims first. No, you don't. You just have to show that it works. You just don't. An electrically driven over unity electrically generator, as I said in November 2 years ago, right, over 2 years ago, is the easiest thing in the world to conclusively demonstrate. It's the easiest thing. It's the absolute easiest thing. So either he's done it and he's choosing not to show it, or he hasn't done it. But I do believe it's possible. I do believe it's possible. Okay, so please go to the. Has anyone got any questions here? Hey Bob, if you can get my radio pop, you will have come out. Okay, cool. Stephen, Bob, do you have any inkling of the pulse frequency? Are we talking hertz, hundreds of hertz, thousands of hertz? Well, if you want to ionize gases, typically you need radio frequency. It doesn't necessarily need to be radio frequency. It will be pulse followed by some frequency after that. But, you know, partly it will be determined by the HID device you use and the gas pressure in there. And these things, what you'll do is you'll set up the device and you'll see what frequency and what tension is required, like how high voltage and how high frequency you're required to go across that. But, you know, our researchers are capable of doing that, and I hope that they will take up the challenge, and I hope globally people will take up the challenge. So I think it might be interesting to do this million pixel graphic and you know, and have the money that's donated in a blockchain that everyone can see. Everyone can see. They know the money's in there. They know it's in there. And if I'm managing that, then they know where I am. It's like I'm not a hidden face. You know where I am. Like if whoever does it, I don't care if it's a member of the MFMP. And bear in mind, I do not give preference to anyone. Right? Like, if I know something, I say to people, like, I'd like to tell you this, but I'm going to tell everyone at the same time. One to many is my viewpoint. That's how I roll. But Rossi could, if Rossi has the goods, he could just walk up and say that, there you go, there's the circuit diagram, and there's the system, and you could test away and confirm what I'm saying. And there he goes. He gets the prize fund. Done. And it's like, it's tested, and he's the person that gets the prize. So obviously, he's the person that did it. But if he doesn't want to hand over those schematics, and he doesn't want to hand over I believe that we can do it. We can light the new fire. We can be the dawn of an old age. We can be the people that create the dawn of the old age. Yeah, you know, Hutchison could do it. You know, he's tooling up. He's tooling up. I believe he can do it. Right, Gordon, good night. If anyone's got any... Okay. The prize, yes, the prize is we all don't die, yes. We survive our catastrophes, yes. If this provides your light, your heat, and your electricity, that is all you need to drive an interstellar system. Now, if you've got the propulsion, that's it. You've got unlimited heat, unlimited light, and unlimited electricity. And the electricity is what you need to drive the system that will extract the hidden energy within matter and provide the propulsion through a range of different ways, suggested by Matsumoto, suggested by Shoulders, and my suggestion as well. We can explore these things. I couldn't do anything right now, WP for Truth. I couldn't really. I'm so tired. I really, all I wanted to do today is sleep, and I was so into talking to Alexander Shishkin, and then I realized it's sort of like 7:30 this evening. I committed to myself that I would talk about EVO Blaster today. I committed to myself that I would do that. It's the 1 year anniversary, and the timing is absolutely perfect with Rossi's presentation yesterday. Absolutely perfect. I couldn't have wished for the universe to come together in this way, other than what I would really have wanted Rossi to do is say, this is what I'm using, it's this simple, what I'm doing is I'm using this frequency at this pulse rate to stimulate heat, in this frequency and this pulse rate to stimulate electricity production. I'm using this frequency and this pulse rate to produce UV or other photons, which I can use or down convert into the visible spectrum to produce light. And it's these ratios and these are the equations that I use in my system to be able to switch between the different parameters. And this is the concept on which I've done my level best to put into the public domain things that would describe the process. And, you know, so he picked up on, anyway, it doesn't matter. He's had literally every single opportunity to say how this works. And I read the room yesterday, and I thought, I don't think the community is going to take another hit of this. I just don't think they're going to do it. So we need to do this. We need to do this as a collective. Well, if you create a ball lightning, it spins, and you can see on the Klimov presentation. And let me see if I can pull that up. Actually, if I've still got Klimov's presentation here. Okay, I'll just pull this up because it's important. Has he got it here? Yeah. In Klimov's presentation, this is the plasmoid here you're seeing, and this spins round in a high speed, and it produces this pulsing here. So this is where you would harness your energy from this plasmoid here, and you could pick it up in a variety of ways. You could rectify it. You might want things like high power Schottky diodes, something like that. That's how I was considering doing it when I was in India in 2017, a whole series of Schottky diodes. You need very fast response and so on. And in fact, it was an equivalent of a Schottky diode. It was a hairpin diode that was used by Moray in his device. But anyway, you could use the Solin method, which is to put one big fat induction coil around it, and gather the oscillation that comes from the spinning plasmoid. So there's a ways you can do this, but you really want to try and suspend the plasmoid between the two electrons between the two electrodes by feeding it at the right rate, and that's where your control system would come in. Good, join the technicians. That's a good ambition. Yeah, so yeah, you're picking up the. There's several ways. You will have electrons emitted from ionization. You will have electromagnetic as well, and so on. There's several different ways you can harness the energy. Obviously, photons. It depends where you're driving it to. Where you're getting more photons that are in the visible range or UV range or X-ray range. Yeah, people have probably got all sorts. The funny thing is, over the last year or so, I bought quite a few of the type of electronic little boards that I would need if I had the time to produce this. But my view is, my time is better spent trying to clearly lay out the science behind it, so that more people can explore the actual making the deliverables, really. Great, Dan. It sounds like you've got a tool there that could be good for stimulating this. So certainly the barrier to entry is very, very small. the cost of these HID controllers, I mean, they're for use in cars, so you can buy them. You can buy the 35-watt controller, and I think I even saw a 100-watt controller and two 100-watt controllers and two light bulbs, or at least one and 100-watt bulb for like $75. So there's, great WP for truth, yeah. But please don't. It has to be one to many. All the time you give it to a little clique of people, then those clique of people will try and capitalize on it and cut you out of the loop. You just need to give it to everyone all at the same time. Just get it out there. Great, Mescal. Great. Xenon? You can go out and buy half the components I'm talking about from your local electronics store and you know, car light bulb fitters. You know, your the local shop that puts fancy stuff on your car. David, I don't think you need an element. I think what you need is you need these. You just need a Xenon 12 volt bulb. Like, you can buy these kits. There's a million and one, and this is probably almost exactly what Rossi has. He has one of these in the box with the bulb, and it's already got the Xenon in there. You don't have to buy it, and you know, this is a probably a 35 watt unit here, the ballast, and it's 516 rubles. There we go. If you're in Russia, here's a 100 watt driver. It's got the cables, like everything's set up for you. It's just here's a nice big HID. You don't need a big one like that. I would start with something small like this. You know, this is what is that? That's like $14 for the bulb. You know, the eminently replaceable. very, very nice. And like I say, you can get phosphor once you got it working. You can look at phosphors for downsampling the X-rays and I've talked about literally everything you needed to know over years. Anyway, there we go. I you might have missed it, David, but I dropped out. Oh, you can't see the screen, can you? Sorry about that. I'm talking about these. This is a Xenon Ballast 35. This is probably the same unit that Rossi used. Here's some 100 watt ones on the right here, close up, and this is the sort of thing where you've got, like, this is the 35 watt one, and this is, you can imagine this square box with the plastic around it, and that's the unit, and it's glowing blue, and it's glowing blue because he's working it in the UV range. Yeah, done. Oh dear. And it's exactly what I shared, like, back in the beginning of 2018, saying, look, this is what John Hutchison uses. He uses a massive great HID lamp in his experiments, and this will be producing exotic vacuum objects. And by the way, it's got Xenon in there, and that's what Ken Shoulders used. Done. Yeah, it's not expensive, but it's not simple. And this is why I think it might be fun to have a little bit of a competition. I think it might be fun. And like the first person to lay out because you can't patent this. I basically said the whole scientific principle behind how it works, other than just finding out the frequencies. And I'd be surprised if you could patent the frequencies. Anyway. You got a 35 watt one. There you go. You're right in there. Hi, Mr. Bannister. It's fine. You can go back. It's a video. You can go back and watch it anytime you like. It's a paddle wheel that taps the Cosmos flow. Yes, I do believe this is able to cohere very clearly. And I've told you why before, and I'll go into it again when I've got the energy. But there's very clear signs that this is cohering matter from the cosmos. Would you consider appearing on the Singularity Lab podcast? Yes, and you know why? Because when you blow up one of these things, like an Evo Blaster, it'll send out an EMP. What will that do? That will destroy artificial intelligence. We are the best device for a consciousness container. We are the best device. Things designed on silicon and gallium and so forth, they will fail easily when this technology is prevalent, when it's ubiquitous. They won't be able to survive. So forget the AI singularity. In fact, there's one way around it. You could embed the AI in humans. you could put something in the body and make the humans the AI, do it the other way round. And I think I was about, I don't know, 12 or something, and they were going on about how the population in Japan was aging, and that they needed to develop robots so that they could look after the aged population. And I thought, I never understood the point of making robots like humans. Why don't you start with humans and make them stupid? And I thought, that's a terrible thing to say, but it's the obvious way to do it. Why spend so much effort? And I thought, that is just, I just thought that is just such a horrible concept. But that might be what they're trying. It might be what they're trying. So, you know, I'll say it again. The silicon chip inside her head is switched to overload. And nobody's gonna go to school today. They're gonna make them stay at home. 'Cause daddy doesn't understand it. He always said she was good as gold. 'Cause he can see no reasons. 'Cause there are no reasons. What reasons do you need to be shown? Oh, 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 oh. Tell me why I don't like Mondays. Tell me why I don't like Mondays. Tell me why I don't like. Tell me why I don't like Mondays. Yeah, it was the first mass school shooting. It was a girl. She's still in jail. And I think it's prophetic. The silicon chip inside her head was switched to overload. Oh, we don't like this person. They didn't vote the right way. So I have no problem talking on a podcast. Okay. Okay, I'm going to have to go to bed because I've got family duties in the morning. It's family day tomorrow. So thank you very much. I'm not sure what I'll do on Sunday. I wanted to expand out the solitons from the last presentation. I think probably I need to owe you the proper edit of the APEC meeting. But I might do the Shishkin work anyway. So because I think it really ties off this, and you're going to see. Yeah, this really is how it works. Anyway, so thank you very, very much for your time. It's been a pleasure, really, to get this off my chest. It's been a pleasure for me to get it off my chest. I really, really, truly wish that Rossi could have been more open, you know, with every single iteration of his journey. But logically speaking, there is a mechanism by which this can be achieved, and I would like to probably see this competition put together. I haven't named. I don't know whether I have a domain that I could probably use and put up this picture. And if anyone wants to put money into the pool fund, then we can do that. And you know, I think the world out there would greatly benefit from this technology being open. And you know, if you are an expert at doing this, you're going to be the person that makes products that work because you understand it at a deeper level. But you know, no one's paying royalties for lighting fires. No one's paying royalties. No one's even paying royalties for the internal combustion engine. You know, there might be better cars and worse cars, but the actual internal combustion engine, and this is our birthright. This is something that our species has used before. It's our birthright. We almost certainly used it to get to this planet, and we have to use it to save this planet and stop the nonsense that's going on. And this is a call to arms. This is a call to work together and put your ego to one side. I've done this amazing thing. No. Rossi had the opportunity. But anyway, whatever he did, I have to give him credit. He accidentally left enough to show, you know, at least where he thinks he is, or at least what he thinks he's doing. But the evidence is there across more than one century that this is possible. And we know we've used it before because you just have to look at the archaeological record and it's unbelievably consistent. And when the military are telling you this is how you should be doing it, and we have these patents and they're all kind of in the same area, then this is how it works. And so, you know, let's go ahead and do it. So thank you very, very much for your time, and I will see you in the next video. Bye-bye for now.